Okay, welcome back. This is our fourth and final part in this segment on energy, enzymes, and thermodynamics. Today we're going to look at enzymes, and we are going to look to see how enzymes affect the energetics of those reactions that we looked at earlier as G varied as a function of the reaction progressing from start to end. So let's get to it. So what we're going to do here is we're going to use a concrete example to look at this, and we're going to look at the reaction in which glucose and ATP are reacted together to produce a molecule called G6P. That's glucose 6-phosphate, and also a molecule of ADP. So our reactants here are glucose and ATP, and our products are G6P and ADP. Now, this is the first reaction in glycolysis, and we'll talk about glycolysis next time, or in our next set of videos when we look at cellular respiration. And the enzyme that catalyzes this reaction is called hexokinase. Now, this actually proceeds as two sets of reactions, but we're going to consider it as one reaction, and we're going to look at the energetics of how this reaction as it proceeds, and we're going to look at the effect of an enzyme here, and then we'll compare the energetics of a reaction without an enzyme and a reaction with an enzyme, and we'll look to see how they differ. So what's this enzyme hexokinase doing here? Well, here's hexokinase, the enzyme. Remember, enzymes are proteins. They've got three-dimensional shapes, complicated structures, and they have these things called active sites. And the active site is where the reactants will bind. So this is where glucose and ATP will bind. So here's our glucose molecule here. Here's our ATP molecule here. And these are going to both bind into the active site of the enzyme. And once that happens, we get what's called an enzyme-substrate complex. And once the reactants or the substrates are in the active site, the enzyme does some chemistry, and is what we're going to have happen is one of these phosphates, one of these yellow balls, is going to be transferred onto the glucose. So here in the next stage, we can see one of these yellow balls of phosphates being transferred from ATP, and that creates ADP, and the phosphate that ends up on the glucose gives us glucose 6-phosphate. And when the chemistry is being done, we release the products ADP and glucose 6-phosphate. So what is the enzyme actually doing here? Well, it's actually doing three things. So we'll compare what an enzyme does to how reactions occur in the absence of enzymes. So reactions do a few things. The first thing they do is they bring the two substrates together, because the active site fits these two substrates. In the case of hexokinase, it fits ATP and glucose. It's got two little pockets, and they fit right next to one another, and so the two substrates can bind in there, and so they're put right next to one another. So that's the first thing to do. The substrates are brought close together. Chemicals and molecules, they can't react unless they are brought together and brought into physical contact. So if they're just floating around, they're not going to be able to react. They've got to be touching, and so the enzyme brings them together. The second thing the enzyme does is it holds them in just the right conformation. It's just the right way. So if I want to react two things together, let's say I want to react this part of a molecule. Imagine this is a part of a molecule and this is a part of a molecule. If I want these two things to react, it doesn't work if this happens or if this happens. I've got to bring these two things together so that a reaction can occur to produce a product. So the enzyme is going to hold the two substrates in just the right way, so the reactive chemical groups, the functional groups we've talked about before, can be close together. So there's two things it does to start with. It brings the substrates together so they're in the same place, they're in physical proximity, and it orients them so they are able to chemically react with the functional groups that need to react held close to one another. And then the third thing it does is an enzyme will actually change shape slightly when the substrates are bound. And so people like to talk about this lock and key mechanism, and that's just wrong. Is what happens when substrates bind to an enzyme, the enzyme kind of changes shape a little bit. So the way that I think about this is if you've ever put your hand inside of a baseball mitten, you know how you kind of get it in there and it's not quite right, and you wiggle your fingers around and then it's kind of fit in there, your hand's in there nice and snugly. That's what an enzyme does with its substrates. So the enzyme would be the mitt, and the substrates would be your hand going in there. And so when the substrate goes in there, there's a little bit of movement and shifting, and the enzyme is what it's doing then is it's straining the covalent bonds which are holding certain parts of the molecule together that need to be reacted. So in the case of ATP, it's straining the bond between the two end phosphates so that one of those phosphates can be broken off and given to glucose to make glucose 6-phosphate. So those are the three things that an enzyme does. It brings the substrates together in one place, so they're not just floating around, and if they float around, it takes them forever to come together. It holds them so that the groups can react properly, and it strains the covalent bonds so they're more easily broken by putting in a small amount of energy. So what is the net effect of that? The net effect of those three things is that enzymes speed up chemical reactions. They are biological catalysts. Now, chemists love catalysts, bless their souls. They love catalysts. Probably the most famous catalyst is heat. And so if you take two molecules which are going to react very slowly and you heat them up, they will react much quicker. So what is happening there that is being replaced by the function of an enzyme in a biological system? Well, if you heat something up, if you heat up a solution of two chemicals which are going to react, as you heat them up, obviously the temperature goes up, and that's a measurement of the amount of kinetic energy in the system. So now these molecules are colliding with one another much more frequently because they're moving faster. And the more times they collide, the more likely they are to be just in the right orientation. And so you get a much faster reaction rate. Now, biological systems can't be heated up. They don't tolerate that. Bad things happen to enzymes and biological systems and membranes and things when you heat them up. So we have biological catalysts, enzymes. Enzymes are usually proteins, but there are some really interesting cases where enzymes aren't the only catalysts involved, and actually RNA, so nucleic acids in the form of RNA, can act as biological catalysts. And we'll talk about that when we talk about translation a little bit later. In fact, if we go back and we think about very early events in the origin of life, it was probably a catalytic RNA that was the first enzyme. So when we say enzyme, we're talking about a biological catalyst, generally a protein, but we could be talking about a catalytic RNA as well. And we'll talk about that when we talk about transcription and splicing too. Okay, so let's now look at what the enzyme is doing in terms of the energetics of a reaction. So this slide's a little bit busy. I apologize, the word enzymes has popped off the top, but you can read it. There's no problem with that. So here's our hexokinase enzyme. We've got ATP again, we've got glucose again, and in they go to the active site. Let's look at the reaction without an enzyme. So that is the red line. So the red line's under the blue line here. So here are our reactants at the start of a reaction. Here are our products at the end. That would be G6P and ADP. And over on the y-axis, we've got free energy, just like the graph we've seen before. So what's going to happen here? Okay, so without an enzyme, is what happens is we've got to put some energy in, energy in, energy in. Those bonds are going to start to, if these two molecules, ATP and glucose, can contact one another, if we put some energy in, enough energy in, they'll collide in just the right way, bonds will break, new bonds will form, and there will be this release of energy that comes out. And so what we've got is products with a lower value for G at the end here than the reactants have at the beginning. So a small number minus a big number. So what you can see is the change in free energy here is going to have a negative value, less than 0. So this reaction is actually exergonic. This first reaction of a glycolysis is exergonic. So what happens is we've got to put in this much energy all the way up to here if we don't use an enzyme. That point there at the top of that red curve is called the transition state. And the amount of energy you've got to put in to get the reactants to the transition state, that's the point when they react. So at the point they react, that's the transition state. So that amount of energy we've got to put in from the reactants, starting with the reactants amount of energy, it's called the activation energy. So without the enzyme, it's this amount here. You can see this arrow here. That's the activation energy without the enzyme. What about with enzyme? What's happening there? Okay, in goes the energy, but well, look, we've got to put in much, much less. Why is that? That's because the enzyme is doing the work of bringing the reactants together and orienting them appropriate and straining the bonds. Now without an enzyme, you're just got to wait and wait and wait and wait and wait, or you've got to put in more and more and more energy. So you've got to put in more energy ultimately. If you wait longer and put the same amount of energy in, that's more energy. If you just put more energy in so that it goes at the same rate, that's more energy. So we've got to put in this much energy with an enzyme. Now let's look at the products. Here's the key thing. It doesn't matter whether you use an enzyme to get the products or whether you just wait. And you wait many hundreds of thousands of years. It doesn't matter how long you wait, whether it's a quick reaction with an enzyme or a short reaction, or whether it's a long reaction, absence of an enzyme. G in the products doesn't change. G is going to stay the same. One of my students once said to me, Duncan, this is obvious. It's because you've got what you've got. The reactants are the reactants, the products are the products. An enzyme doesn't suddenly make you have different products than a reaction that's not catalyzed by an enzyme. So the enzyme's not changing the G of the reactants or the G of the products. It's not changing the sign of delta G. The only thing that's happening is you don't have to put as much enzyme in, as much activation energy in. So with the enzyme it's this much, without it is this much. Now, is what we're looking at here on this axis is just progress. Start is here, finish is here. Is what I would like you to do is actually draw this graph with time on the x-axis. So what would this look like if you drew time on the x-axis? Draw that, put it in a discussion in Canvas, and we're going to see what you guys come up with. So that's a lot of material. That is complicated. You probably have to go through and watch that again and draw that graph out. Okay, so enzymes have these optimal conditions that they work at. For example, a normal enzyme in the cytoplasm of your cell is going to work at about pH 7.4. An enzyme in a lysosome is going to work at a much lower pH, probably around between 4 and 5, that kind of pH. Enzymes that work in your stomach are going to work at pH 1 to 2, much lower acidity, very high proton concentration. So enzymes have these optimal conditions, and temperature is an optimal, needs to be carefully controlled. This is one of the reasons why if you get very high fevers, you end up dying. It's because membranes stop functioning properly because their fluidity changes, but it's also because enzymes start to stop working because they become denatured, they basically fall apart. So if we look at an enzyme in a human, let's just say in a regular cell, not in any unusual compartment, just in the cytoplasm, its optimum temperature is 37 degrees Celsius. And if you kind of drop below that temperature, it doesn't work as well. So this is the rate. Rate drops. If we go over that temperature, rate drops much quickly. So what you notice is the rate drops off much quickly above the optimal, but it slowly ramps up as we move towards the optimal. So why do we have this weird shape to this curve? So let's see what happens at 0 degrees Celsius. At 0 degrees Celsius, freezing basically, molecules have very little kinetic energy. As we start to heat the system up, they get to 10 degrees Celsius. Now the molecules are moving around more freely, they've got more kinetic energy, so they're colliding with the enzymes. The reaction rate goes up a little higher at 20. More and more kinetic energy going into the system. The reaction gets to a point where it's optimal. At this point, it's going to go as fast as it can, given a certain substrate concentration. Now, as soon as we push it over that and we come up to 40 degrees Celsius, something's happening. So my question to you is, why do enzymes very quickly stop working when you go above their optimal temperature? Now, think about enzymes in the case of proteins. What happens to a protein if you heat it up? Think about those bonds we talked about in protein structure. Give this one a go, and I'll flash the answer up in a moment. Okay, like always, folks, I'm going to direct you to the learning outcomes. There is a lot of stuff in your textbook, a lot of stuff you'll find online that I've not really covered here. I am doing bare bones stuff, the really most important stuff, the hardest to understand stuff. A lot of stuff in the learning outcomes. Review those. If you're having problems with them, into discussion. Come to office hours. Meet with Leslie. Meet with the TA. And we're going to wrap that up here, and next time we come back we're going to start talking about the mechanics of cellular respiration, and the way that I'm going to do that with the videos will be a little bit different, so expect something a little bit different when we get into the next set of content, which is cellular respiration. I will see you soon.